Hello everyone. We have discussed about the density of energy states in our previous class, that is in the free electron theory of metals. But I think we should spend little bit more time on that subject because the density of energy state concept is a very important one when we are studying the solid state physics. Since we are discussing about the metals, so we should know what is the importance of calculating density of energy states for metals. So if we go through properly, we can find out that if we know the density of energy states for the charge carriers in metal, that is for the electrons, then we can also able to calculate the number of electrons within the metal. We can also find out the Fermi energy and calculate the average kinetic energy of an electron or average velocity. So these are the importance of density of energy states when we want to study the metals. So next we would like to find out what are the possible steps to calculate the density of energy states. In this context, we also focus on the difference between the energy level and energy states. Sometimes it comes to our mind that why we are so interested to find out the density of energy states rather directly count down the number of energy states. So we will follow up all these points through this discussion. But first we move to the free electron theory of metals. As per this theory, we know that the valence electrons, which are shown as red dots in this diagram, are free within the metal, but they cannot escape through the metal surface. This problem is quite similar to the problem in quantum mechanics, that is the free particles in three-dimensional box. So if we can replace our real problem to the problem in quantum domain, that is the free particles in three-dimensional box, and if we solve the Schrodinger wave equation for these free particles, here free particles means electrons, we can find out the allowed energy levels for that electrons. Not only that, we can also find out how these free electrons are distributed in different energy levels. That is, for example, if we think there are n number of electrons inside the metal, n number of free electrons inside the metal, and if we convert this real problem that n number of electrons are in three-dimensional box in quantum domain, then if we solve the Schrodinger equation, we want to find out how this n number of electrons will be distributed among different energy levels. So first we will not proceed for n number of electrons and their three-dimensional case. So rather we would like to move that how this n number of electrons are distributed if they are confined within a one-dimensional box. So for simplicity or to simplify our problem, we will move from three-dimensional to the one-dimensional case and from one-dimensional to three-dimensional to find the real picture. So let's move to the next slide. So here we would like to know the distribution of n electrons in different energy levels when they are within a one box. That means how n number of electrons will be distributed among different energy levels, and here we are considering this n number of electrons are in one-dimensional box. But we will further simplify our problem that initially we will not take n number of electrons, rather we will only take the single electron, and we want to find out what is the behavior of a single electron if it is inside a one-dimensional box. From the diagram we can see that this free electron is confined with a one-dimensional box of dimension L, and at the edge the potential is infinity. So the electron will be free within the box and it cannot be escaped from the box. In this case, the Schrodinger equation for this free particle or free electron becomes d2 psi k dx2 plus twice m by h cross square ek psi k equal to 0. What is the m? M is the mass of the free particle or electron. Ek is the total energy of the electron when it is in the energy level k. If we solve the Schrödinger equation, we will find out the expression for allowed energy values, which is given here, that is Ek is equal to h cos square by twice m k square. With proper boundary condition, we will find that k is equal to n pi by l, and n is a positive integers. That means n can take values 1, 2, 3 and so on. In terms of n, we can write this energy expression as En is equal to h square by 8m l square n square. L is the dimension of the box. So according to the different values of n, we will get different values of energy levels. So what we have observed here, we have seen that the energy spectrum of the free particle when it is inside a one-dimensional box becomes discretized. That means the energy of the free particle will remain in different discrete energy level. But in classical mechanics, we have seen if the particle is free, then it can take any values of energy. That means its energy is continuous. But in quantum mechanics, we have seen the energy is not continuous, rather it is in discrete form. And there is another observation that the energy level separation depends on the factor n square by l square. Since we have seen En is equal to h square by 8m l square n square. So the spacing between two energy levels depends on the factor n square by l square. If l is large enough, then the spacing between them very less and the energy levels are closely packed or closely spaced. So we have seen in this slide that what is the behavior of a single electron when it is within a one-dimensional box. But our aim is to find out what will be the behavior of n number of electrons when they are inside a one-dimensional box. So let's move to the case for n number of electrons. So here in this diagram, we can see that in place of one electron or single electron, there are large number of electrons within this one-dimensional box. Now our task is that how this n number of electrons can occupy different energy levels, or how this n number of electrons can be distributed in different energy levels, because we have the energy expression is n is equal to h square by 8m l square n square, and if we substitute different values of n, that is for n is equal to 1, we will get the ground level energy E1 is equal to h square by 8m l square, and if we put n is equal to 2, we will get the second energy level is 4 times of the ground energy level, and so on. So now our task is that how these electrons will be distributed among these different allowed energy levels. The problem becomes very easy, or problem how to tackle this problem, we will use the Pauli exclusion principle. What is that? We know according to this principle that each energy level contains 2 electrons, and what is the condition? That for that 2 electrons, all 4 quantum numbers should not be equal. We have, or we know that there are 4 quantum numbers n, l, ml and ms. These represent the energy state of an electron. And what is the condition to fill up one energy level? That all these 4 quantum numbers should not be equal for these 2 electrons. That means if we consider n is equal to 1, that is the ground energy level, we can see from this diagram that if n is equal to 1, then L, that is azimuthal quantum number, is 0. magnetic quantum number is also 0, but ms should have two different values if we take the upward spin, and there must be another is the downward spin. So for this energy level there may be two energy states. So these are the energy states, and each energy state contains a single electron. So you should take care in this point. This n is equal to 1 is the energy level. So this is energy level, but each level may contains two energy states according to two different spin quantum number. That is, if we consider the first electron, that means if we think that initially in this one dimensional box there is no electron, first we want to drop this are splitted in different energy levels, and we want to drop this electron in this potential box. What will be its possible position in this energy levels? So it is obvious that these electrons would like to occupy the lowest energy level, that is the ground energy level in this case, and for that ground energy level n is equal to 1, and let's say its spin quantum number is plus half, which is along the upward direction. So it will occupy this energy state, but the energy level is n is equal to 1. If we consider the second electron now, so first electron occupy n is equal to 1, that is E1 ground level energy, and now we are considering the second electron where it will be situated or where it will be placed for the second electron. If for that electron it can also take this ground level, but there should be one condition, that all the four quantum numbers should not be equal. That means if the second electron want to be placed in n is equal to 1, that is ground energy level, L must be 0, ml is 0, so all three quantum numbers are same as like the first electron, but here ma should be minus half. If it is so, then the second electron will also occupy the same energy level. So this is the Pauli exclusion principle to fill up the energy levels. So at the ground energy level there will be two energy states, and each energy state contains a single electron. So let's try to understand, if there are n number of electrons at absolute zero, that is T is equal to 0 Kelvin, how this n number of electrons will be distributed among different energy levels. What we have seen, each energy level may contain two electrons, but their spin should be opposite. So if we move following the Pauli exclusion principle, that if there are n number of electrons, then each level contains only two electrons, then there will be n by 2 field energy levels. How is it possible? We have seen that two electrons are in one energy level. That means one electron will be 1 by 2 energy level, and n electron will be at n by 2 energy level. So if there are n electrons, only n by 2 energy level will be filled up at absolute temperature, and the maximum filled energy level is called the Fermi energy level. So what we have observed here, at absolute zero, according to the classical mechanics, the energy of all electrons should be 0. At absolute 0, energy of the metal or energy of the electron should be 0. But at absolute 0, what we have found out, that the energy of the electrons should have a range, and the maximum energy will be of the Fermi energy level, and it is near about 5 electron volt for most of the metals, or average Fermi energy level at absolute zero is equal to 5 electron volt. So classically the energy should be zero, but quantum mechanically we have seen at absolute zero there may be a maximum energy of the electron which is about 5 electron volt, and this is the main or basic difference between the classical and quantum mechanical behavior of the free electrons. And the next thing is that number of electrons is the number of energy states, or in terms of energy level, number of electrons is equal to n by 2 energy level. So if we know how many electrons are there at absolute zero, we can also find out how many energy level will be filled up by these electrons. So it becomes very easy to count the electrons in terms of energy level. Now we would like to know our final aim, that is what about the n electrons when they are 3D box. So far we have discussed that n electrons in one dimensional box. Now we would like to find out if n electrons are in 3-dimensional box, what will be their field energy levels and what will be their allowed energy level.